Around IT in 256 seconds by Tomasz Nurkiewicz. Episode 59. How compilers work.
A compiler is an application that turns text into an executable program. It's quite extraordinary how much work these complex pieces of software are doing. Pretty much every compiler works by executing several phases. Each phase takes the input of the previous ones to finally produce the runnable code. Let's take a journey through the compiler internals. The compiler's work is traditionally divided into three stages: front-end, middle, and back-end. The front-end interacts directly with the source code. It reads your C++, Rust, or Go file. At this point, your source code is just a sequence of characters, or even bytes to be precise. The first phase is tokenization by a so-called lexer. A lexer takes a stream of characters and groups them according to the language rules. It uses regular expressions for that. For example, there's a regex for all keywords, number literals, operators, etc. White spaces are typically ignored by this phase unless they are significant. So, if your source code is answer equals 21 times 2, for a typical language, this will produce a stream of the following tokens: an identifier named answer, assignment operator, number literal 21, multiplication operator, number literal 2. Answer equals 21 times 2. At this point, many syntax errors are caught. The next phase of the front-end compiler is parser. The parser takes a flat stream of tokens and organizes them in an abstract syntax tree. Within that tree, functions and operators are parent nodes. Arguments are children. In our assignment example, the assignment is the parent node. One child is the identifier, answer. The second child is a subtree. That subtree has multiplication as a parent node and numbers 21 and 2 as children. This weird tree structure supports operator precedence, parentheses, and overall is quite convenient. At this point, many errors are caught. For example, the first child of the assignment operator must be an identifier, a variable. The next phase is semantic analysis. Here, the compiler checks types and other programming language constraints. The middle end of the compiler takes the raw syntax tree and optimizes it. The optimizations include dead code elimination, pre-computing constants, etc. All optimizations are agnostic to the target machine or processor. The result of this stage is the so-called intermediate representation, IR for short. For example, bytecode in Java may be considered IR. The backend compiler takes IR and produces the machine code. First, it applies optimizations specific to selected CPU architecture. Say, if you are targeting a 64-bit CPU, different optimizations are possible. Similarly, some techniques faster on x86 are slower on ARM, and vice versa. Last but not least, the backend compiler generates machine code. It still requires a lot of work, like organizing data in CPU registers. Finally, a standalone executable is produced. Keep in mind that many languages these days aren't compiled ahead of time. For example, C# or JavaScript. C# is compiled to IR. JavaScript is distributed as source code. The compilation typically happens inside a browser, and it's just an optimization technique known as just-in-time compilation. That's it. Thanks for listening. Bye.